Alright, I just discovered the wonders of cut and paste, so I'm going to try this super difficult Mac Daddy. Forget I said Mac Daddy. I'd rather you guys didn't think of me saying such horribly dated words. So, I'm going to try this problem though, where we have these two objects. One of them is being pinned to a wall, the other one's just sitting on top of it. This force is what's holding it to the wall, so we're going to have all kinds of stuff. There's this question about friction, I don't care. I don't give a damn what kind of friction you're talking about, so just shut up. But it is accelerating and does have some velocity. We'll say the velocity is up the wall. I mean, all we're told is it's greater than 0, but we can assume that means up the wall. So I am going to first define my coordinate axes. We're going to go like that, x and y. So there we go. So there's this force here acting on M2. We got that. We've got the weight of M2, which is going to be acting down. We've got the weight of M1, which is going to be acting down. We've got a normal force here that M2 is going to exert upwards on M1, right? And then the wall is going to exert a normal force on M2. There's going to be friction, and we'll say if it's moving up, the friction then is acting downwards, the normal force. And I think that's all the forces we've got. So, that's it, just 6 forces, two objects. So let's do our free body diagrams. So let's do the FBD for, we'll start with the FBD for mass 1 because that's easy. So here's our, y and x, and mass 1, as there's our, dot to mean mass 1. That is the weight of mass 1. So I'll call it W sub 1 equals M1G. And then we have the normal force, and that's, I'll call that N12. So it's the normal force between mass 1 and 2. All right, well that's easy, and these are both vertical. So right away we can write our Newton's second law equations for mass 1, which go something like this. So sum of forces in the x direction. No, sorry, there are no forces at all in the x direction. So you know what? Screw it. Don't even bother to write the equation in the x direction because it's 0 equals 0. Sum of forces in the y direction, on the other hand, equals we've got N12 going up, N12 minus this weight of 1, which is M1G, okay, and that's going to equal mass times acceleration. What mass? Well, mass of 1, because that's the object we're talking about, right? So times the acceleration. We assume these two are both accelerating upwards, the same rate. So there's your equation of motion or there's your force balance equation for mass 1. Pretty easy. All right. Let's do the FBD for M2. A little more challenging. There's your Y, there's your X. So here's our M2 dot. Let's see, what's acting on that? Well, we've got let's see, looks like we're going to have the force F is acting. So hang on, let me see if I can draw that decently there. At an angle theta. That's our force F. There it is. Make a bigger dot so we have room to hang a few more things on. This is the weight of mass 2 equals M2 times G. Okay, so that takes care of this and this. We have the normal, well, we have the weight of mass 1 is pushing down on it. So up on the top we have the weight of mass 1 equals, is that right? Let's see. So the weight is pulling down on it, the normal force is pushing it. No, I'm sorry, that's not what we have. We have the normal force between 1 and 2 acting vertically. That's it. So right here at the interface, M2 gets pushed down on by the normal force between 1 and 2. Okay. And then we have the normal force between 2 and the wall, which I'll just call N2W, I guess. I don't know. And finally, going downward, we have the friction force, F sub F. So we've got 3 forces going down. We've got one going to the right. That's the normal force. And then we have this one at an angle going up here. So now we have to do our component resolution free body diagram, which is really not terribly hard because almost all these act in one direction. So I'm going to draw us a nice big circle here so we can get this one right. So there's our force due to friction. There is our weight of object 2, which is M2 times G. And finally over here on the right is our normal force between object 1 and object 2. Here's our normal force between object 2 and the wall, pushing object 2 outwards, like that. And then finally, we have this F, which we resolved into components. So this is F sine theta here, right? And F cosine theta going up because adjacent to the theta, Okay. So, and there is our free body diagram for number 2. I am going to, just to keep myself a little more space, I'm going to make this F cosine theta over here. Okay, so let's find our, so let's see, let's just draw a line here and say all this is for mass 1. And let's do for mass 2, why did I write an E? I have no idea. So we'll do sum of forces in the x direction equals, so we have this N normal force between 2 and the wall, right, N2W, minus F sine theta. So that's just this going to the right, this going to the left, and that equals 0, right, because there's no acceleration in the x direction. Easy enough. And then let's do sum of forces in the y direction. So we've got this F cosine theta going up. Okay, and then down we have, oh boy, we have minus force of friction, we have minus m2g, and we have minus normal force between 1 and 2. And that is almost, we're right about the edge of the screen there, I think. So it's going to equal mass of 2 times the acceleration. And those are our equations, really. These ones right here go to object 2, and this one up here goes to object 1. And those are our three equations of motion there. We could probably, well, I don't know if we could solve the problem yet or not, but yeah, there you go. So that's all solved. I mean, that's the free body diagrams and the equations of motion, which is what we wanted.